Hi, everybody. Here is the remaining notes for Chapter 3, Section 1. We're on example number 6 right now. We need to find the domain and the critical values. Remember, the critical values are where the derivative equals 0 or where the derivative does not exist. So let's take a look at letter A. So the domain for this polynomial is going to be all real numbers. And so our critical values will be when f prime of x equals 0 and when f prime of x does not exist. Well, since this is a nice polynomial, it's continuous, there's no vertical asymptotes, there's no corners, there's no cusps. We're not going to have any critical values from where the derivative does not exist. It's going to exist everywhere. So now we're going to find where the derivative would equal 0. So we're going to take and do the power rule. So this is going to be, 4 times a half, which would be 2x to the third minus 3x squared minus 2x. And we're going to set that equal to 0 and solve. We're going to take an x out of everything. So this will become 2x squared minus 3x minus 2 equals 0. And then we are going to factor that. I have done the factoring in the trinomial method for us already. So the factors are going to become x times 2x plus 1 times x minus 2 equals 0. So your critical values are x equals 0, x equals negative 1/2, and x equals 2. Alrighty, for letter B, the fastest way to do letter B, quite honestly, is to just graph it. We know that this is an absolute value function. If we rewrite it this way, it might be a little bit easier to think about what's going on. So we are going to be shifting to the right 4 units, up 2 units, and this is going to be reflected over the x-axis. So let's see here. If we reflect, this is going to end up like this. So 1, 2, 3, 4, 1, 2, like that. And it's going to have a slope of down 1 over 1. So it kind of goes like this. And so the critical points are going to be where the derivative equals 0 and where it doesn't exist. So the derivative does not equal 0 anywhere on this graph. This is a positive slope, so that's going to be a positive derivative. This is a negative derivative. We don't have a spot where it doesn't, or I'm sorry, where it equals 0. The spot that we are concerned about is where it doesn't exist, and that is going to be right there, and that's at the x equaling 4 points. This would be over 4 and up 2, so your critical value would just be one spot, and that would be at x equals 4. For letter C, also for letter B, I didn't talk about the domain. The domain is still all real numbers for letter B. Any x value is going to work in that absolute value equation. Alrighty, so for letter C, you have x to the 3/5. Remember, you could rewrite that as the 5th root of x cubed, if you wanted to, times 4 minus x. This is an odd root, so you can have negative numbers under here, and so no problem with that. So your domain is still all real numbers. We're going to take the derivative and see if there's a spot where it doesn't exist or where it equals 0. So your derivative, we have to do a little product rule. I wonder if we could just, actually, we don't have to do product rule. We could distribute this. All right, so back up just a second here. Let's distribute this. This would be 4x to the 3/5 minus, let's see. So that would be 5/5. So 3/5 plus 5/5 is 8/5. So x to the 8/5. Alrighty. So when we take the derivative of this, you would bring the 3/5 out in the front. So that would be 12/5 x to the negative 2/5. And then minus 8/5 x to the 3/5. So we're just carefully working with those fractions. 3/5 times 4 is 12/5, and then 3/5 minus 1 is -2/5. And then 8/5 comes out in the front. 8/5 minus 1 is 3/5. So let's see here. That is the same as saying 12 over 5 fifth root of x squared, like that, minus 8 over 5. This can stay in the top. So fifth root of x cubed. All right. So where does that equal 0? Well, you have two fractions there, and I'm running out of space. Probably combining them would be ideal into one. Let's see if I can do that in this little bit of space here. We need to have a 5 fifth root of x squared as the common denominator. So that means we need to multiply this 12 by the fifth root of x squared, and then this would be minus 8 fifth root of x cubed. All right, where the derivative is not going to exist is a little bit easier than where it equals 0. It's definitely going to equal, well, it's definitely not going to exist when the denominator of this equals 0. So that's going to be when x equals 0. So f prime of x does not exist when x equals 0. Let's see here. What can we do with this? We could take out a GCF from these two. They do not like terms, so we cannot just like subtract these roots. But you could take out, well, we could take out a 4, and you could take out a fifth root of x squared. So this would become 3 minus 2. And then if you have a fifth root of x squared and you need a fifth root of x cubed, it would be, you need another fifth root of x, like that. So that would be the numerator, okay, just the numerator. The bottom would still be 5 fifth root of x squared. Now, to find where this fraction equals 0, you're going to set the numerator equal to 0. We're going to throw out x equals 0 because we already know that that's where the function does not exist. You're going to set this part, there's just this 3 minus 2 fifth root of x, set that equal to 0 and solve. So it looks like you're going to have fifth root of x equals -3 over -2. So those will turn positive. And then you're going to raise both sides to the fifth power. So 3 to the fifth all over 2 to the fifth. And whatever that comes out to be. I know the bottom is 32. 3 to the fifth would be, let's see, 3 squared is 9, times 3 is 27, times 3 is 81, so 243 over 32. That will be your other critical value. That was definitely a challenging one. Okay, so 2 critical values here and here. Alrighty, so there's some information in the box that you should take a screenshot of or write down on some index cards. These are your steps for finding absolute extrema. So first of all, identify the endpoints. You always include the endpoints in with your critical values. Then find critical values, and you do that by taking the derivative and setting it equal to 0, and also finding where the derivative does not exist. After you get those critical values, you are going to plug them back into the function. And your biggest value is going to be your maximum. Your smallest value is going to be your minimum. And then obviously answer in a nice, professional, complete sentence. Okay, so let's put this together and try these next examples. All right, so I'm going to switch to pencil. Alrighty, so determine if the EVT applies. If so, find the extrema of the function on the interval. So you have 3x to the fourth minus 2x cubed, and you are on this closed interval. So this is continuous because it's a polynomial. There's no asymptotes, there's no holes or any kind of jump discontinuities. We are on a closed interval, so that means that EBT does apply. Okay, those two things are satisfied. So now we are going to find critical points. Remember, start with the endpoints. So x equals -1 is a critical point, and so is x equals 2. Now we're going to use our derivatives. So find where the derivative equals 0, and also find where the derivative does not exist. Okay? Well, we know that this is a polynomial, and so it is smooth and continuous. The derivative is going to exist everywhere, so there will be no spots where the derivative does not exist. Let's take the derivative. So this would become 12x to the third minus 36x squared. Set that equal to 0. Factor out a 12x squared. You're left with x minus 3. That equals 0. So far, we have checked off that we're continuous. We're on a closed interval. We included our endpoints as our critical values, and now we are looking at when the derivative equals 0 and where the derivative does not exist. We know since this is a polynomial, the derivative is going to exist everywhere, so no worries with this. Now we're working on solving this. So if 12x squared equals 0, x is going to be equal to 0. The other critical value is going to be x equals 3. Okay, so we're going to add these to our list. X equals 0 and x equals 3. Now you are going to plug each one of these into the original and get an answer. So f of -1 is going to give us 15. Let's see here, where can I put this? F of -1 is going to be 15. F of 2 is -48. F of 0 is 0. And F of 3 is -81. So remember, these are your maxes and mins, the actual y values. So the biggest answer is your max, which looks like 15. That's going to be your maximum. And your smallest value is your min. So this is your min. So you have a max of 15 occurring at x equals -1. And you have a min of -81 occurring at x equals 3. Okay, and that question's done. Let's look at example number 8. Determine if EBT applies, and if so, find the extrema on the interval. Well, we have the closed interval, so that's checked. Now we have this. Is this continuous? If that helps you, you can rewrite it as a radical. X to the 2/3 is going to be the cube root of x squared. So you want to think about, is there any domain restrictions on this? Can I put negative numbers in here? Does 0 work here? I don't have a fraction, so I don't have to worry about that. You can put negative numbers in here because they will turn positive, and a cube root would allow for a negative radicand anyway. So your domain is all real numbers. And this also is continuous. There's no spots where there's going to be a hole or an asymptote or anything like that. Alrighty, so now we include the endpoints. Don't forget the endpoints. So x equals -1 and x equals 1. Now we are going to take the derivative, set it equal to 0, and also find where the derivative does not exist. Now, this might not be a nice smooth curve. It's continuous, but there could be some points, especially with this radical, makes me think there might be a cusp. So we are going to check for where the derivative does not exist. Okay, so let's take the derivative. So this is going to be 2 minus 2/3 times 3 is 2. X to the, subtract 1 from here, -1/3. That equals 0. So this would be the same as saying 2 minus 2 over x to the 1/3 power, like that. If you want to change it into a radical, you could. I think I'll do that. So this is the cube root of x. So we're going to subtract 2, and let's see what happens here. So -2 cube root of x equals -2. I could divide both these by negatives, make that positive. That's nice. I could cross multiply. So here and here. So 2 cube root of x equals 2. Divide by 2. Cube root of x equals 1. Cube both sides. So x equals 1 is one of your critical points. Oh, we've got that already. Alrighty. So is there a spot where the derivative does not exist? Well, let's go back to this right here, okay? We don't really need the equals 0 part, but I want you to go back and just look at the expression right here. So this has a fraction. Let's get these two having a common denominator here. So the common denominator would need to be cube root of x. Now, the second one has the cube root of x right there, so that's just going to stay at 2. But this was over 1. So if I multiply by cube root of x on the bottom, I need to multiply by cube root of x on the top. Okay? So the main idea here is, and we did get that down here, that's the numerator, 2 cube root of x minus 2, but the denominator is cube root of x. And so you have this rational expression representing the derivative. Okay, remember this all came from taking the derivative. We're not really concerned about it equaling something. This is just the derivative rewritten as one big fraction. That's all that is. I want to know where this doesn't exist. Well, this doesn't exist when this fraction is undefined. So you have a cube root, so you can take the derivative, you can take, you can take the cube root of a negative number, no problem. But we can't have 0 in the denominator. That's what I'm getting at. So the derivative is not going to exist at x equals 0. If I plug 0 in here, then you're going to have an undefined fraction, and so therefore the derivative isn't going to exist. So you have critical values at -8, +1. I got the +1 down here, so I don't have to write that twice. And then x equals 0. And now you're going to plug them into the original function, okay? So f of -8 gives you -28. F of 1 gives you -1. And f of 0 is just 0. So the biggest answer is your maximum, and the smallest answer is your minimum. So this is going to be your max, and -28 is going to be your minimum. So I don't know if I can squeeze it in here anywhere, but you're going to have, let's see, I guess I can put it right here. So you're going to have a max of 0 occurring at x equals 0. And you're going to have a min of -28 at x equals -8. Okay? And on to example number 9. All right, so for example number 9, you're going to determine whether or not EVT applies. So we have the closed interval, so check. And then this function is a trig function. All right, all trig functions are continuous on their domains. And so the domain for sine is all real numbers. The domain for cosine is also all real numbers. If the domain is, when you subtract two functions that have a domain of all real numbers, the final result is also a domain of all real numbers. The only one you really need to worry about is tangent, because we are only continuous from negative pi halves to pi halves. But this is good to go right here. So yes, EBT does apply. Yes, EBT does apply. Oh, I did not write I did not write yes up here, did I? It does. So remember, EBT just guarantees that we're going to get a max and we're going to get a min out of this. So we are going to look at where, we're going to include the endpoints. Almost forgot about that. So x equals 0 and x equals 3 pi halves. Okay? So now you're going to take the derivative and you're going to set it equal to 0, and you're going to look to see where the derivative does not exist. Now, since sine and cosine are nice, smooth, continuous functions, then 2 sine x minus cosine 2x is also going to be a nice, smooth, continuous function. So the derivative is going to exist everywhere. You don't have to worry about looking where it doesn't exist for this problem. So what we do need to do is take the derivative and set it equal to 0. So this is going to be 2 cosine x. And then let's see, a little chain rule going on here. Derivative of cosine is negative sine. So this would be like negative, negative. So plus 2 sine 2x. Don't forget we had to take the derivative of this. That's why there's a 2 in front of that. All right, now we are going to set that equal to 0. Now I'm going to let you in on a little secret here. I'm going to use a trig identity for this. This is a double angle formula for sine. So I'm going to recopy 2 cosine x plus bring that 2 down. And then the double angle formula for sine is 2 sine x cosine x equals 0. That is a popular one to memorize, this one right here. Now I can factor out a 2 cosine x from both of these terms. So 2 cosine x, parentheses, 1 plus, let's see, I took one of these 2's out already, so I'm left with 2 sine x equals 0. Now you're going to set each factor equal to 0 and think about your unit circle. So 2 cosine x equals 0. 1 plus 2 sine x equals 0. Divide by 2, cosine x equals 0. Where does cosine equal 0? It equals 0 at pi halves and 3 pi halves. And since pi halves and 3 pi halves is contained in this interval, those two are also critical points. Over here, if we subtract 1 and divide by 2, you have the sine of x equaling negative 1/2. Where does the sine equal negative 1/2? Well, it's going to be in the third quadrant and the fourth quadrant. But we cannot include the fourth quadrant because 3 pi over 2, so this is pi over pi halves, pi over 2, pi, and then 3 pi over 2 does not include the fourth quadrant. So we need to think in the third quadrant, what would be the angle? What would be the angle? So once again, 3 pi over 2 stops right here, so we don't have the fourth quadrant. We need the angle in the third quadrant that has a sine of negative 1/2. The reference angle is going to be pi over 6. So let's see, pi plus pi over 6 will be 7 pi over 6. So x equals 7 pi over 6. So we've got lots. We've got 1, 2, 3. Don't have to count that one twice. 1, 2, 3, 4 critical points. So we're going to plug them into the original. Remember to always plug into the original. So f of 0, when you plug it in, is negative 1. F of 3 pi halves ends up being negative 1 again. F of pi halves is 3. And f of 7 pi over 6 is negative 3 over 2. So the biggest answer is your maximum, and the smallest answer is your minimum. So this one's going to be your max, and this is going to be your min. So you're going to have a max of 3 occurring at x equals pi halves. you're going to have a min of -3/2 occurring at x equals 7 pi over 6. And that's example number 9. Example number 10, you're going to find the extrema for each of the functions over their domain. Notice these have domain restrictions. We can sketch the graphs also. So this domain right here, you have a radical in the denominator and of a fraction. So that means that this has to be greater than 0. Can't even be equal to 0 because we can't have 0 in the denominator. So that's going to make this right here cannot be -2, and it also cannot be +2. You can go through and check this using your pre-calc, making the number line, but our domain is going to end up from -2 to +2. Now, when you do that picture, and you can put this in Desmos, 1, 2, -1, -2, 2, -1, -2, is going to look like this. So, and I think it's gonna, let's see, 0, yeah, at 0, it's gonna be like 1/2. So this is actually 1/2. It's gonna dip down, gonna dip down like that.
Student drivers.
Oh, it's the end of the day. All right, I can get this done. So you're gonna have this picture, and based off of the picture, you're gonna see that this is gonna have a minimum at x equals 0. And when you do f of 0, that is going to be, let's see, put min right there, 1 over square root of 4 minus x squared, like that, which would be 1 over 4 minus 0 squared, 1 over square root of 4, which is, that's where we get that 1/2 from. So a min is at x equals 0, and it is 1/2. All right. For letter B, we are going to do a piecewise function. And so for the piecewise function, you're going to have a parabola that is upside down and then a straight line. So you have 5 minus 2x squared. At 0, this is going to be up 5. 1, 2, 3, 4, 5, like that. And then so that's going to be, let's see. Oh, we want to go all the way to 1. So right here at 1, put a 1 in. So this would be 1 squared times 2. So up 5 minus 2 is 3. 1, 2, 3. So right like this. So our parabola is going to do that. Now, for all x greater than 1, it's going to be this line. So plug the 1 in. This is going to be at 1 plus 2, which is 3. They actually join up at the same spot. And then it's going to have a slope of up 1 over 1. So that's your picture for letter B. You can see that you're going to have a local max and a local min. There's no absolute max or absolute min for these. Notice that. We also did not have an absolute max for example number 10 because of these open circles. But you're going to have a relative max and a relative min. So, or you could say local max and min. So local max is 5, and that is at x equals 0. And then a local min is 3, and that's at x equals 1. Notice your local min occurred when the derivative does not exist because that is a pointy cusp right there. And your local max occurred when the derivative was equal to 0, that nice flat spot up there. All righty, everybody. Bell's going to ring very soon, so I'm going to try and get this one in before that bell rings. Example 11, using your calculator's equation solving capability, holy moly, not just its max min finding ability, find the extrema. Okay, so are we on a closed interval? Yes, we are. Are we continuous? Yes, this is a continuous function. You don't have any asymptotes. You don't have any gaps, no problems whatsoever. E to the x is always continuous. And so if we rewrite this, well, let's see, f of x is going to be x e to the negative x minus 2x. We could write that as x over e to the x minus 2x like that. When you take the derivative of this, what do we get? Let's see, I'll do product rule. So this will be the derivative of x times e to the negative x, which is e to the negative x, plus the derivative of this, which is going to be negative e to the negative x times x, like that. And then the derivative of minus 2x is just minus 2. That can be written as 1 over e to the x minus x over e to the x minus, well, we could actually make this 2 look like this, 2e to the x all over e to the x, getting a common denominator between all of these. This one, I didn't have an e to the x in the denominator, so I had to put one there, which meant I had to multiply by e to the x. Alrighty, so now put this into your calculator or Desmos, and then look for the x-intercepts. So this is going to be 1 minus x minus 2 e to the x all over e to the x. When you put this into your calculator, look for x-intercepts. We'll pick up with this next time we chat. Have a good one, everybody.